And okay, all right. So today we are talking about clustering. We're going to introduce k-means clustering and unsupervised learning. Okay, so let me just start off talking about unsupervised learning. So, well, in contrast that to everything we've done so far, which has been supervised learning. Okay, meaning you have the target value, your output value y or t or whatever it might be, and you have your input values x, right? And so everything we've done, whether it be linear regression, the neural network, the classification stuff, you have the input values, and then you have your output values. And we have a way to measure the difference between what our model predicts. We have a way to measure the difference between the predicted value and the target value. And we want to minimize the difference between our predicted and target value. And so that's measured with a loss function. And we try to optimize the loss function so it's as small as possible. And that guides the training of our model, okay? Today we're going to look at unsupervised learning, okay, and we're going to look at k-means clustering, which is kind of the simplest version of this. And what we're doing is we're looking for structure in our data based on the input values alone. We have no output column y or t or whatever you want to call it. There's no output values. There's no target values. We only have the input matrix X, okay? And based on the input matrix X, we want to find some structure. We want to, in our case, we want to cluster. We want to group similar observations together. Or later on, there's other unsupervised methods such as dimension reduction, okay? Dimension reduction counts as unsupervised learning. And we'll take a look at that, okay? So clustering is, I think, what it sounds like, which is you're going to try to create clusters. You're going to try to create groups of objects or observations that are similar so that the difference between the observations within a cluster are small and the difference between the clusters is great, okay? So you want similar objects to be together and different objects to be in different clusters, okay? So you have, how do you measure similarity, okay? And that's a question. Today, with k-means clustering, we're going to measure similarity using Euclidean distance and things, but there's different ways you could measure similarity, right? And there's all kinds of applications of this, right? So pretty much recommendation engines and or like grouping similar products together is some form of clustering, okay? So, you go on Amazon and you say, I'm going to buy this thing, and Amazon says, hey, you should also buy this thing, or maybe you would want to buy this thing, and it's grouping basically similar purchases together. You can group documents together this way, like if you go on a news website and you read an article and it says, hey, maybe you're interested in this, things like that, okay? You can even group physical locations together, which is part of what powers, on Uber and Lyft and these rideshare apps. There's often a pool option where it's going to try to match you with other riders that have similar pickup and destination locations so that it can kind of group you guys together and get two people's fares with one and pay only one driver type of thing, right? So what it's trying to do is clustering there, okay? Maybe it's not motivated entirely by money. Maybe they're trying to reduce the environmental impact by grouping similar rides together also. So anyway, today we'll look at k-means clustering, okay? K-means clustering is kind of the simplest of the clustering algorithms. And the way it works is it's going to say objects are similar based on Euclidean distance, right? So we've got some input matrix X. Your input matrix X is going to, we're assuming it to be all kind of numeric values. And so if you have categorical variables here, and you need to do a clustering algorithm or something, you have to find a way to turn those categorical values into numeric values. And there's lots of ways that can be done, but that's more of a feature engineering topic and not something that we're talking about right now. Okay, so we got numeric values, and we're going to measure similarity in terms of Euclidean distance. Okay, so I want to just say don't mix up k-means clustering with k-nearest neighbors. Okay, they both have a k in the name. They both use Euclidean distance, but other than that, they're very different, right? So k-means clustering is unsupervised. We don't have the labels, okay, and we are just looking for structure. K-nearest neighbors is a classification method. It's supervised. We have the labels of what things should be, and we run it that way. So so despite having a k, the k stands for different things, right? Well, I mean, a k is just an arbitrary number, but k nearest neighbors, the k is how many neighbors you're looking at. K-means is the k there is how many clusters you're looking for. Okay. In k-means clustering, clusters are defined by the centroids. Okay. So the centroid is going to be the center or the mean of the points that are assigned to the cluster. Okay. And the formula for finding the centroid is the sum of z sub nk times x sub n divided by the sum of z n sub k. So so basically znk is equal to 1 if object n is in cluster k and 0 if it's not. So you're gonna, so basically every observation has a z value for each cluster k. So if you're looking at cluster k, okay, z is going to be 0 if an observation does not belong to cluster 1, and it's going to equal 1 for an observation that does belong to cluster 1. Okay, and basically what that means is you're going to take you're going to multiply 0 for any x that's not in the cluster. You're going to multiply x by 1 for any observation that is in the cluster. So you're going to get the sum of the x's that are in the cluster, and you're going to divide by it, and then the sum of the znks will be basically equal to the number of points that are currently in the cluster. Okay, so this is what we have. Okay, when you run the algorithm, it's going to look like this. Okay, so step 0 is you have to decide how many clusters you're going to look for, the number of clusters to look for. You need to do that before you run your algorithm. We'll talk about some strategies or some ideas behind picking the number of clusters, but this has to be determined beforehand. Okay. First step is you're going to take your data and you're going to randomly assign the values in your data to one of these clusters, okay? To each of these clusters k, you just do it randomly or arbitrarily. And then once all the values have been assigned to a cluster, then you're going to calculate the centroid of the values in each cluster. Okay? And then after that, you reassign values to clusters by associating each value or each observation to the nearest centroid, okay? And the nearest is going to be using the Euclidean distance. So you assign each observation to the nearest using Euclidean distance, okay? And then you repeat steps 2 and 3. So you go back once all the values have been assigned, calculate the centroid, and then step 3, reassign the values by associating it to the nearest centroid. Keep doing steps 2 and 3 until you reach convergence. Convergence occurs when no values get reassigned. All right, so we're going to start off with this very simple toy data set. Okay, and here in this toy data set, I've got 8 data points, 0, 0, 0, 1, 1, 0, 1, 1, 3, 3, 3, 4, 3, 3, 4, and 4, 4. Okay, 8 data points, and then we're going to look for 2 clusters here. All right, so this is how the data comes in. It comes in unlabeled. Nothing says this one belongs to cluster 1 or this belongs to cluster 2. If we look at this with our eyes, our brains are already kind of tuned to cluster groups together, and we would say, okay, this is a cluster and this is a cluster, right? Our visual processing capabilities say, okay, I see 2 clusters right away. And we're really good at that. And in the illustrations I have today, it's all going to just be, it's going to be 2-dimensional. But k-means clustering can work in higher dimensions as well, okay? And our brains aren't so good at higher dimensional clustering here, okay? So, so anyway, the first step is we're going to randomly assign some of the values to one of the 2 clusters. So we're going to say we're looking for 2 clusters. We randomly assign the values to either cluster 1 or cluster 2, okay? So, okay, yeah, sorry. Step 0, we're going to say, pick how many clusters we're going to look for. We're going to look for 2 clusters. And then we're going to randomly assign the points to a cluster. Okay, so here I just do sample 1 and 2. And we're going to assign that, create assignments out of that. And then I'm going to create my Z1 and Z2, which will be, is the assignment equal to 1 or is the assignment equal to 2? So, so here, this is what we get. We randomly assigned these 5 data points to red. The other 3 data points get assigned to black. Those are our current cluster assignments, okay? So 3 got assigned to black, 5 got assigned to red. It doesn't matter that a different number got assigned to the different clusters. That does not matter. And what we do is we calculate the centroids of the values in each cluster. So, so here we can see these are the X values. We got 0, 0, 0, 1, 1, 0, 1, 1, 3, 3, 3, 4, 4, 3, and 4, 4. These are our 8 observations, X1 and X2. And we can see here is the column of assignments. This observation is assigned cluster 1. This observation is cluster 1. And this observation is cluster 1, okay? And so for the Z1, I get 1 for everything that's in cluster 1. 0 for everything that's not in cluster 1. For Z2, I get 1s for everything that's in cluster 2. And I get 0s for everything that's not in cluster 2, okay? So what we do is we take the sum, we basically multiply the X times the Z's, and we do Z times X divided by the sum of the Z's. So if I do this, 0 times 1 is 0. And then I just look for all the Z's that have 1s. I get 1 times 1 is 1, and 4 times 1 is 1. So I get 0 plus 1 plus 4 divided by the sum of Z's, which is 3. And the mean for X1 is 1.667. I do the same thing for X2, and it's also coincidentally 0, 1, and 4 divided by 3, 1.667. We do this for cluster 2. And I get 0 plus 1 plus 3 plus 3 plus 4. 0 plus 1 plus 3 plus 3 plus 4. I have 5 observations or 5 values in Z2, so that comes out to 2.2. I do the same thing with the X2, and I have 1 plus 0 plus 3, 4, 3, okay? 1, 0, 3, 4, 3, also coincidentally equal to 2.2 for the mean, okay? If you use dplyr, this can be done very easily, okay? You can just run dplyr. You can do group by assignments, and then you can say calculate the mean of X1 and calculate the mean of X2. And we get the same values, 1.67, 1.67, 2.2, and 2.2. Okay, so that's convenient and easy, but you can also do it this way as well. All right, so if I graph these are our 2 centroids, 1.67, 1.67 here, and 2.2 and 2.2 here. And what we are going to do is we are going to go through every single observation. For every observation, we say which centroid is closer. So we're going to start here and we're going to say which centroid is closer. Is the black centroid or the red centroid closer? So we measure the distance from this point to here, and we say, okay, well, the black centroid is closer. So it gets assigned to black. We do this next, same thing for the next observation. We say which centroid is closer, black or red, and we say, okay, well, the black one is closer, so that gets assigned to black. We do it for this point. Which one's closer, black or red? Black is closer. Which one's closer, black or red? Black is closer. Okay, this point, which one is closer, red or black? So using Euclidean distance, the red centroid is closer. Which one's closer, red or black? Red centroid is closer. Which one's closer, red or black? Red is closer. Which one's closer, red or black? Okay, so these are the assignments that we get after taking each data point and assigning it to the centroid that is closest. Okay, and then after we do that, we recalculate the centroids. Okay, so now that I have each x value and their new assignments, we're going to group by the assignments, calculate the centroids. The centroid of cluster 1 is 0.5, 0.5. The centroid of cluster 2 is 3.5, 3.5. And so here are our observations with each centroid. And we would technically run through this one more time. I'm not going to do that. But we would ask, okay, which point is closer, black or red? And for all of these data points here, all 4 of them, the black centroid is going to be closer. We ask the same thing for all of these ones. For all 4 of these data points, the red centroid is closer. And we say, okay, have any assignments changed? No, none of the assignments would have changed, and therefore we would say it has converged. Okay, so I guess you would run it one more time and you would say, have any of the assignments changed? And if not, then you can say our algorithm has converged. Okay. Do we have any questions here? Does this feel good? All right, let me give you the first quiz answer. Today's first quiz answer is C as in cat. First answer for today's quiz is C as in cat. All right, so let's try this with, just a slightly more complex example. It's still quite simple. It's only in 2 dimensions. And here I've generated, when I generated this data, I used 3 kind of distributions, and I'm just mixing them all together. So when I generated it using kind of three clusters, and this is kind of the data points that were generated from each of the 3 clusters. So I put I think I said, generate some points from here, and this is, these are the points it generated. It just said generate some points here, and these are the points it generated. Generate some points, and it did this, okay? Again, when the data comes in an unsupervised learning thing, though, is that none of these points are classified, okay? There's no labels. It comes in completely unlabeled, and what we're going to do is we're going to say, let's look for clusters, and there are, I'm going to say, look for 3 clusters in our data. And our very first step is to just do random assignments. Okay, we're going to just randomly assign each data point to either cluster 1, 2, or 3. Okay, and so this is what we get when we randomly assign our data. So it's randomly assign clusters 1, 2, and 3. This is what we have. And so this looks like a mess, and that's fine. Okay. And then what we do is we run through and we say, okay, what is the mean of all of the black points? What is the mean of all of the red points? What is the mean of all of the green points? And we calculate the centroid of basically each cluster. Okay, so the points are currently assigned randomly to different clusters, and we're going to calculate the centroid, just the mean of each of these things, okay? And so because it's random, we get slightly different values, okay? And so let me just kind of graph this. And this is what we have, okay? We have the mean of all the red points is right here. The mean of all the black points is like very similar, but a little bit off. And the mean of all the green points is over here, okay? So it's random. They end up similar, not exactly the same, but similar, okay? And so now what we do is we're gonna ask, we're gonna reassign all of our data points to belong to the cluster whose centroid is the closest, okay? So we're going to start, with one of the data points. We say, okay, which centroid is closest, right? And so we measure the distance and we go, okay, green is the closest, black is next, red is the farthest, okay? The difference between the distance to green and red is not great, but we would definitely say green is the closest centroid. And we go through every single data point, and pretty much all of these data points over here is going to say green is the closest and red is the farthest, okay? For all of these points over here, we say, okay, well, which centroid is the closest? We're going to come over here. And we go, oh, red is the closest. Green's a little farther away. Black's a little farther away. So pretty much all of these data points will get red assigned to the closest, okay? And then we have to say, okay, and there's only going to be a handful of points in here that will say black is the closest centroid. So I think this point right here, if we measure which centroid is the closest, I think it's going to say black is the closest centroid. Probably this point also, black is the closest centroid. I'm not sure. I think this one is going to say green. That one might be green or red. I'm not sure. Okay, but we're going to go through and we're going to say, all right, which point centroid is the closest one? Closest one. Okay, and after we do that, this is what we get. So all of these ones said green is the closest. All of these ones said red is the closest. Apparently for this one, when we measure the distance, black is the closest centroid. Green's a little bit farther away, okay? All right, so we've done all of the reassignments. Black hardly has any points assigned to it, but it's okay. It doesn't have 0 points assigned. So what we can do is for each cluster, we're gonna recalculate the centroids. So we're gonna say, where is the mean of all of the green points, right? So we say, what's the center of all of these green points? Probably somewhere around here. Okay, we're gonna look for the mean of all the green points. We say, what's the mean of all of the red points? Probably somewhere around here, not 100% sure, okay? And what's the mean of all of the black points? Okay, well, there's only a few black points. Probably the mean is gonna be somewhere around here, okay? So then we go to the next slide and we say, okay, where we plot the centroids, okay? And we say, okay, here is the center of all the green points. Here's the center of all the black points. Here's the center of all the red points. Okay, and then what we do next is we say, all right, let's reassign points. We're going to go through and we're going to say, okay, which centroid is the closest? Okay, so still for all of these, green is the closest. For all of these, red is the closest. But now, some of these points, black is going to be the closest, right? Like this observation, black's the closest centroid. For these observations right here, black is the closest centroid, okay? Even for like maybe this one, let's see, red looks like it's going to be a closer centroid. But for this one, black's going to be the closer centroid. And pretty much we have to kind of find the spot halfway between black and red. And probably these ones will go to red. These two will go to red. This one will go to black, right? So that's how I'm imagining some kind of split here. We do the same thing for green, and I think these 2 points will go to the green centroid. And I think, let's see, well, I'm not sure. This one could go to black or green. I can't tell. But this one will definitely get assigned to the black centroid. Okay, so if we look at this point, this one's the mystery one. Okay, basically the ones to this way will go to green. These ones this way will go to black. I think, just visually, I think this one will go to green. I'm not sure. But anyway, we'll go to the next slide. Yep. And that's what we see. These ones go to green. These ones went to black. Okay, over here, yep, this one went to black. This one went to red. Okay, so here the points after we reassign them. And then we say, okay, now that we've reassigned these to the centroids, let's recalculate the centroids, right? So we say, okay, what's the mean of all of these points? What's the mean of all the black points? What's the mean of all the red points? We calculate the centroids, and this is what we have, okay? And then we go through the process again, and we say, let's reassign the points to the nearest centroid, okay? So these points used to belong to red, but I think they're going to get reassigned to black. These ones also. This one could go either way. This one could go to red or black. I'm not sure. It looks like it'll stay in red, okay? And we'll do that. I'm curious about this one. I'm going to guess red, and I think pretty much all of these ones will go to black. I think we're going to get a split like right around here. Okay, I think these two will go to green, and I think these ones will go to black. This one I think will stay red, but let's see. Yep, that one stays red. These ones go to black. Oh, and actually, these ones stay green, and these ones went reassigned to black. And then we recalculate the centroids again. Now that we've done some reassignments, we go here, and then we do some reassignment. Okay, we reassign some points. And did anything change? Actually, these two changed. So I need to do one more iteration technically, okay? So I would reassign points, and if nothing changed, we would say it has converged. Actually, two changed, so I probably need to do one more iteration here. But if we, after this one, I'm pretty sure it stays converged, okay? And so we would say, so this has converged. If no points get reassigned, the data has converged, and that would be the solution of the k-means clustering algorithm. And we'll say these are the three clusters that we have found. What we can do is we can compare, because we know the data that was generated, we can compare our clustering results with the generated data, okay? And this is what we have, right? So when we generated the data, this point actually came from the red cluster, right? But when we clustered it, it got assigned to the black cluster, right? But we could understand that if we're using Euclidean distance, this point sure looks like it's a little bit more similar to the center cluster than the red one, okay? But when we generated data, it didn't do that, okay? So when you do k-means clustering, it's just gonna assign points to the nearest cluster using Euclidean distance, right? So it has really no other way of measuring similarity, okay? That's the simplicity of the k-means clustering algorithm. And I do want to say that just by coincidence, the clusters that our algorithm chose are red, black, and green, and their color labels just happen to match the generating color labels. But this is not always going to be the case. Whenever you do clustering, the labels of the clusters are completely arbitrary. Okay, when we clustered this, we could have very easily, like, this could have been called green, this could have been red, and this could have been black. Okay, and it doesn't matter. Okay, it just means here's a group, and here's a group. There's no significance associated with the label of the cluster or the color of the cluster. Okay, so coincidentally, they happen to match up, but this is not always going to be the case. All right, here in R, there is a k-means function. K-means will perform k-means clustering. And so here again, what I said about the labels don't matter. In the original data, we called this red, black, then green. When we did k-means clustering in R with k-means, we got green, black, red, okay? I think same result as our own clustering, but just you know, different colors here, and but the same clustering results there. Okay. In your next homework assignment, I'm going to make you write some code to perform k-means yourself, okay? And I think that will really force you to think about how the algorithm works, and you'll work through that. Obviously, in production settings, you're probably gonna just use k-means. Don't generally rewrite code that already exists, okay? But for your homework, as part of kind of a learning exercise, I'm gonna make you write some code to produce the k-means algorithm yourself. But you know, in production settings, just use k-means. It works. It runs for R, and it works well. So anyway, in R, you just run k-means. You give it the data. In our case, it's just the x1 and x2 columns. Okay, and then you say how many clusters you want to find, and it's going to search for 3 clusters here. Okay, super simple. The results are in results $cluster, whatever it is, the output $cluster, and this is what it looks like. If you take a look at the output of the k-means clustering, okay, it's going to produce the cluster means. So here we've got 3 cluster means: 0, something close to 0, 0, 4.5, something close to 0, -4, 0. I think the original data was produced with means 4, 0, and -4, 0. But this is, it's the results. These are the assignments, okay? And I think in the original data I had all the data, these to be 1s, and these to all be 1 cluster, and these to all be another cluster. And so we could see, you know, maybe this one got put in the wrong thing, and you know, there might have some error there, but who knows, okay? And another thing to look at is this. This is kind of, it's like an R² value, sort of, okay? So you think of kind of the total sum of squares, and you know, in some kind of linear model, you have the between sum of squares and you're within your residual sum of squares, and basically the between plus the within add up to the total, right? And so what we're trying to do is we're trying to minimize the sum of squares within a cluster, all right, which would be basically the distance from every point to the centroid, versus the total sum of squares. The total sum of squares would just be if everything were unclassified and you find the mean of all the data points, which would be somewhere probably around here, and you find the sum of squares, square distances to the one centroid, that would be the total sum of squares. And so anyway, we want to minimize the residual sum of squares or maximize the between sum of squares. And so if we do between sum of squares divided by total sum of squares, we get something around 86.2. Okay, and that would be kind of our conceptual equivalent of an R² value for the k-means clustering algorithm. Okay, there's a whole bunch of other stuff, right, that comes in. So if you look at the structure of k-means, you get basically the list of clusters, the list of centers, or the matrix of centers. The total sum of squares is this, within sum of squares is this, and between sum of squares, if you do total within sum of squares, you add them up, and you add the between sum of squares, these two numbers add to each other, okay? And it says, you know, we found the algorithms within a couple iterations and things like that. Okay, I want to show you what would happen if you use the wrong number of clusters. So here, or I don't know, right or wrong number of clusters, that's okay. The right or wrong number of clusters, this is a hard question, and there often, if you have unlabeled data and you're in an unsupervised situation, you don't know how many clusters to use. That's part of the problem. And so there's actually not really an answer to what is the right or wrong number of clusters. So, so here, let me just show you what happens with 2 clusters. With 2 clusters, this is the result. We have a center at 3.4 and a center at -3. between divided by total, kind of our R-squared value is around 70%. Compare that to 86.2%. So we have a much lower R-squared value, okay? And if I plot this, this is what it looks like, all right? So it says, you asked me to find 2 clusters. This is what I've done. And you know, if we find the centroid of these points, it'd probably be around here. All of these points are closer to this centroid. All of these points are going to be closer to this centroid. Okay, so that's the result with k equal to 2. All right, let me show you. If I do k equal to 4, we've added another cluster, and these are kind of the results. The between sum of squares is right here, 87.8. So if we compare that to using 3, we went from 86.2 to 87.8. Okay, so just marginal improvement. Like if you, and we know that if you keep adding points to a cluster, or adding parameters to a model, you can always inch up your R-squared value, and that's basically what's happening here. And this is the result. Okay, so we got a cluster here that looks similar to the first. We have a cluster here and a cluster here, and basically we also form some kind of cluster here, and this has reached some point of stability. Okay, where if we calculate the centroid of each of these clusters, they're not going to get reassigned. Okay, each point is assigned to its nearest cluster. However, if I run the same thing again, I do k-means with 4 clusters. So that's what I did here, k-means with 4 clusters. R is going to start off with different random assignments in the beginning. Okay, and because of different random assignments, you can end up with a different result. So here's the result with 4 clusters, and the center cluster got divided into 2, okay, like this. Okay, so compare that to here. We got different clusters were found, okay? This cluster seems to be fairly stable between the, so those kind of remain the same. But, you know, this one got split over here versus over here, and this one got split almost vertically this way, okay? And we got, you know, so the results are different, right? So we ran k equal to 4, and the results are different. And this is an issue that happens in unsupervised learning, is that depending on your starting values, you can end up getting different results. And you know, how many clusters you should have and which arrangement. You know, in both of these cases, these reached some kind of stable solution where, you know, when we said reassign to the nearest cluster, here nothing's going to get reassigned. Over here, nothing's going to get reassigned. They both reached kind of some sort of stable solution, but they're different, and that happens. Okay, it could be an indicator that you know, maybe you're looking for a k that is too high. Or it could also just be, you know, this is just the results. You know, if you think about it, if I said cluster some observations and it's not clear, if I gave you a scatter, you know, if I gave you just these points in the beginning, something like this, and I said search for 4 clusters, you know, people might come up with different results, okay? And that's what's happening. You know, and it, kind of a real life analog would be, you know, there's a question like how many races or ethnicities are there, right? How many races or ethnicities are there? Like how many should you include on like the census form? So I don't know if you guys filled out your census forms, and it asks you like, what is your race or ethnicity? And you answer that. You know, they had a whole bunch of options for you to check, choose from, but it wasn't always that way. The number of races or ethnicities you could select from used to be a lot smaller. And you know, how do you pick how many to choose from? And that's a tough question. Okay, that's a tough question, right? So you could just say, okay, there's only one race, that's the human race, and everybody's human. Very true. Okay, In the United States, you know, if you go back several generations or several decades, you know, they might have just had maybe kind of two, either white versus non-white or person of color. That would be one way to do it. Okay, if you said three, you know, you might pick different, you know, different things. You know, you could have a cluster for like Asian people. That could be one race or ethnicity, but that could also get further divided into, say, East Asian, South Asian, Southeast Asian, even Central Asian. Those would be some possibilities. And if you have East Asian, that could further get divided into like Japanese, Chinese, Korean, different kinds of, you know, ethnicities, and what is the correct number of groups to look for, and it's it's a difficult question, you know. There are, you know, that's it's a tough question, how many clusters to look for, and it's hard to do. So this is what we have. The results of 4 clusters ends up this way or this way. If we run it again, we'll probably get some different results as well. So here I've just run a little bit of code to help us choose how many, what value of k to pick, okay? All right, and so what I'm gonna do is I'm going to look, I'm gonna start with k, and I'm gonna run a double for loop, okay? We're gonna run k from 1 to 10. This is, so we're gonna look for 1 cluster, then 2 clusters, then 3 clusters, then 4 clusters, all the way up to 10 clusters. And then each one I'm gonna run 20 times. I'm gonna run each of these things 20 times. So I'm gonna say, look for k equal to 3, 20 different times. Look, k equal to 4, 20 different times, okay? And what I'm gonna do is the results of each of these things, I'm gonna take the total within sum of squares, and we want this as small as possible. We're gonna see what kind of values we get, okay? So with k equal to these different values, these are just some of the results I get, okay? And we can see when I did like k equals 10 clusters, with each run, I'm getting slightly different within sum of squares values. Similar, but slightly different, right? Here I got 258, here I got 230, 244, 235. Every time I run the algorithm, with 10 clusters, I'm getting slightly different answers. Okay, so here's a plot of all of the within sum of squares results for different values of k, and so this is what we have, okay? And so we could see going from k equal to 1 to 2, there's a huge drop. Going from k equal to 2 to 3, there's also a very big drop. But then going from k equal to 3 to 4 or 4 to 5, you know, every time I'm adding another group to look for, yeah, the overall sum of, within sum of squares decreases a little bit, okay? It's like we're pushing up that r squared value, but, you know, is the change significant or not? That's the other question, okay? And so after k equal to 3, we don't see very much improvement in the within sum of squares measure. So we'd probably, looking at something like this, we'd probably say, let's look for k equal to 3. But you know, if you have a justification, like if you're familiar with the data and you say, yeah, you know what, it makes sense to have 6 clusters, you know, if we think about it, you know, it makes sense to have 6 clusters or something, sure, go for it, okay? But you know, that requires a little bit of subject knowledge, subject expertise that should be applied there, okay? All right, this is all I've got for you today. We'll wrap up there. Oh, the second quiz answer for today, the second quiz answer is B. B as in bear or boy. B as in bear. And I'll release your next homework assignment soon. Again, If you don't recall, I did make a small change in the grading policy, just kind of keeping in mind the struggles of studying at home and all of that. So normally I do not drop any of the homeworks, but this quarter I will drop the lowest of the 6 homework assignments. So if you're struggling, as I'm struggling a little bit, you know, and you feel like you need to just take a break and not do an assignment, that's fine. Okay. So the lowest of the 6 homeworks will be dropped. Of course, I would love for you to do all of your homeworks because I think all of them are good learning opportunities. But I understand it's a tough time for everyone right now. So I will drop the lowest of the homework assignments. Okay. We'll end there for today, and we will see you guys on Wednesday. And hope you guys have a good rest of your day.